The physical units are mostly a type system enhancement. Essentially, you can annotate any type with a physical unit, and then when you work with this type, you also have to use the units for literals. For example, here, when we compare the speed with a number, then we have to also use, in this case, the meters per second. Also, when you assign something, the units have to be used. Of course, you can use units anywhere where expressions are used. We've seen before the decision table, where we have combined the units extension with the decision table extension. Now, let me show you some more interesting things. Let's create some function here, void a function that takes an int, let's say an int 8 with meters per second called speed. And we have a second function. And now we want to call a function. Of course, the type has to be meters per second. For example, we can directly pass in 10 meters per second, and that's fine. But of course, we can also pass in, let's say, int 8 in meters length equals 10 meters. And you can then also say int 8 in seconds equals 10 seconds. You can then simply divide length by seconds. I should have called it time, but anyway, so, well, not the function, right? It's this guy, seconds. And then, of course, the resulting type, when you divide meters by seconds, is that you get something with meters per second. And that is, of course, compatible with meters per second, because if you go here, you can see that it is meters per second, but if you go to the definition of meters per second, this is where it says meters and second to the -1. You can also see here how you define additional units. You can define any derived unit like this. Now, if you have an existing legacy function, the thing is a bit slow again because of the screen recording, which just takes an int 8, then of course you cannot pass in, let's say, legacy function length, because it is the wrong unit. And so in this case, you can do the following. You can use something we call a strip unit, where you can remove the unit from a value, and this way you get type compatibility. In the same way, if this guy were returning, let's say, an int 8, and you want to, let's extract the local variable result, and you want this to be, again, in meters per second, of course you have a problem. But what you can do now is you can do an introduce unit, where you can take this expression and introduce the unit meters per second. So there is these special APIs for kind of unsafe casting units in and out. Of course, you obviously need this to be able to work with legacy code. Also, you can define derived units, like, for example, actually, sorry, they're called convertible units, like kilometers per hour for speed. And then you can define a conversion rule from, let's say, meters per second to kilometers per hour. And I'm actually not quite sure, but it is, I think, the meters per second divided by 3.6, perhaps. And so, in other words, now if you have a value with meters per second and you want another value in kilometers per hour, then, so let's see, speed 1, well, I wanted to define an integer. Speed 1 with meters per second. Speed 1, well, doesn't eat too much. 10 meters per second. And now you have another one int 8 in kmh, kilometers per hour, speed 2. Of course, you cannot just assign speed 1 because that is the wrong type, and also it is numerically different. So what you can do is you do a, not sure if we have, no we don't, so there is a convert unit, so you can take the speed 1 and convert it to meters per second. And what happens here, oh, in kmh, of course. Right. What happens here is that the conversion rule that is defined here is automatically inserted, so you don't have to write down the actual conversion here, but you have to say that a conversion must happen, and that is because this, of course, has runtime overhead. It may have overflow problems and other issues, and so that's why we don't want to make this happen automatically. You have to write it down. Anyway, this was a quick demo of the units feature.